Let's start at the beginning. Number one. A gas absorbs 0.0 joules of heat and performs 30.7 joules of work. What's the change in the internal energy? Remember the formula for internal energy. Right? Heat transferred, work done. And remember, everything, the signs on all the values are relative to the system. So if we're adding to the system, we're doing work on the system, those are positive values. If the system is losing heat, it's negative. If it's doing work on the surroundings, it's negative. So 0.0 joules of heat absorbed. So that's plus. And then performs 30.7 joules of work. The gas performs 30.7 joules of work. So it's working on the surroundings. Right? So that's the only thing left. It's minus 30.7. That's why the answer is D. Okay? Number two. Let's try number two. What is the kinetic energy of 1.56 kilogram object moving at 94 kilometers per hour? All right, kinetic energy. Remember that formula? 1/2 mv squared. But in order to have these units in joules, these units must be in kilograms, and these units must be in meters per second, because you're going to square them. Okay, do we have that? The kilograms is fine. 1.56 kilograms is okay. But the velocity is not. It's 94 kilometers per hour. We've got to get it into meters per second. So this is a dimensional analysis problem at this point. We want to convert hours to seconds. Remember, when you have more than one unit to convert, do one at a time. So let's convert hours. 1 hour equals how many seconds? 60 seconds in a minute, 60 minutes in an hour, 60 times 60 is 3,600. Okay, takes care of the hours. Now we need to get kilometers, right? Numerator, denominator, into meters. 10 to the third meters is 1 kilometer. Okay, so now we can find out the velocity in meters per second. 94, 3,600 divided into it, times 1,000 is 26.11 meters per second. Okay, 26.11 meters per second squared. Okay, so let's square that value and then multiply it by 1.56 and then take half of it. So I get 3 significant figures. 532. 532 joules. Or, looks like it's in scientific notation, so let's do that. 5.32 times 10 squared joules. Oh, kilojoules. All right. Let's go back. If that's the joules, kilojoules, we move the decimal to the left, right? Because as the unit gets bigger, the number gets smaller, so it has to go to the left. 1, 2, 3. So that's 0.532 kilojoules Now in scientific notation, it's 5.32 times 10 to the minus 1 kilojoules. And that makes the answer A. Well, I jumped on the horse and rode off in every direction and didn't ask anybody if they had a specific problem that they wanted to deal with. So if you do, just interrupt me. If you think of one while we're doing this, interrupt me and we'll take care of your problem first. All right. Let's go ahead and do 3. Which of the following statements correctly describes the signs of Q and W for the following? The signs of Q and W for the following exothermic process. It says that that's exothermic. You think it is? Going from gas to a liquid? Right? If we have a gas in here and it goes to a liquid, yeah, it's got to lose heat to go from a gas and condense into a liquid. Right? So Q has to leave. That's exothermic, which means this is negative. At 1 atmosphere pressure and 370 K. Those facts are irrelevant to our question. So we want to find out what's the work. Well, when a gas condenses, what is it doing? Work is being done on the gas. Right? In other words, if we allow this system, and that's what will happen if the gas is allowed to do this in the open, it will shrink. And as a gas reduces in volume, work has to be done on it by the surroundings, which makes this positive. Okay. So that's why the answer is C for that one. This one is fairly straightforward. That one takes a little mental dexterity. Okay. Let's go ahead and do 4. All right. For a particular process, Q equals 20 kilojoules. Okay. And W equals 15 kilojoules. W equals 15 kilojoules. The positive sign is understood. If you don't write a sign in front of a number, it's always considered to be positive. Which of the following statements is true? All right, so how about A? Is A true? Heat flows from the system to the surroundings. If it's positive, heat flows from the surroundings to the system, right? So that's false. Can't be. B, the system does work on the surroundings. B. If work is positive, then the surroundings are doing work on the system. So that one's false. How about C? Delta E equals what? Well, if we add it up ourselves, a positive 20 and a positive 15 is a positive 35. There we go. And that's true. So all of the above are true? Nope. None of the above are true? Nope. Just this one. C is true. Get somebody else join the meeting. Let me see. Yeah, there's Sam. All right. Okay. Which one was that? 4, 5. Let's go ahead and do 5. Which of the following statements is correct? The internal energy of a system increases when more work is done by the system than heat was flowing out of the system. Okay. Okay. So if we have internal energy equals Q plus W, then that says that the internal energy of the system increases. So this is positive. It increases. Under what circumstances? Work is done, more work is done by the system. If work is done by the system, it's negative. Then heat was flowing out of the system. They're both negative. So delta E can't be positive, right? You can't add 2 negatives and get a positive. You can only multiply 2 negatives and get a positive. So this one's false. How about B? The internal energy of the system decreases. Okay, so this time we're going to do negative. Decreases when work is done on the system. Work is done on the system. And heat is flowing into the system. Right? That's just the flip side. You can't get a negative from 2 positives. So that one's false. How about C? The system does work on the surroundings when an ideal gas expands against a constant external pressure. That's definition. That is true. The system does work on its surroundings when the gas expands against a constant pressure. So all the statements can't be true and all the statements can't be false, so D and E are out. That means C is the only possible answer. All right. Let's see. Let's go page. Let me check my copy and see if I've got any more marked off. Let's go to number 7. One mole of an ideal gas is expanded from a volume of 1 liter to a volume of 8.93 liters. So we're going from initial, oops, not pressure, volume. Initial volume of 1 liter to a final volume of 8.93 liters. Okay. Against a constant pressure of 1 atmosphere. 1 atmosphere. Okay. How much work in joules is performed on the surroundings? Is that what's happening? If we're going from 1 liter to 8 liters, yeah, the system is doing work on its surroundings, so that's true. All right. And what are the units? The units are, in the answer, are joules. Right. So we know that we can calculate work as minus P delta V, right? Minus pressure, 1 atmosphere. And change in volume is final minus initial. Right? So what we have is a negative 8 point, excuse me, not 8, subtract 1, 7 14.93 liter atmospheres. But those are the wrong units. What's the conversion factor? 1 liter atmosphere is equal to 101.3, is it? Yeah, joules. So we need minus 7.93. Oops. 93 times 101.3. So that's a negative. See, our units are in standard. Let's see, what did I do wrong? From 1 liter to 8.93 liters against a constant pressure. Yeah, that's right. And then convert. 101.3. Let me do that calculation again. 7.93 times. Okay, I hit the wrong keys. So let's put 80, round it off, 803 joules, and that's negative. Okay, so that's why the answer is B. And that means that, yes, the system is doing work on its surroundings. That number is negative. All right. Let's see. I've got some others marked off, but I want to check. I want to look at some of these to see if there's anything new. What about 9? 9 looks interesting and different. Okay. A fuel-air mixture is placed in a cylinder fitted with a piston. The original volume, okay, the original volume is 0.31 liters. So here's our piston. 0.310 liters. Okay. When the mixture is ignited, the gases are produced and 935 joules of energy is released. So we've got 935 joules released in that reaction. To what volume will the gas expand against a constant pressure of 635 millimeters of mercury? So we've got a constant pressure of 635 millimeters of mercury. Okay. We want to know what's the final volume. So final volume is our question. Initial volume is 0.310 liters, and constant pressure is 635 millimeters of mercury. Okay, I think this is kind of like the problem before, only in reverse. So if it's exothermic to 935 joules, then the value is negative. And we're going to have to convert joules to liter atmospheres in order to fit it into that previous equation. Right? So we need to get rid of joules and liter atmospheres. So 1 liter atmosphere is 101.3. So 935, 101.3 is 9.23 liter atmospheres. Okay, so now we're going to have minus 9.23 liter atmospheres is equal to pressure, but that needs to be in atmospheres, right? .760 is the conversion there, 1 atmosphere. So 635 divided by 760 is 0.8355. 0.8355 atmospheres. Okay, so we got this one, negative 0.8355 atmospheres. And then we got a final pressure, final volume that's unknown, minus 0.310 liters. Let's look at the question again. To what volume will the gas expand? So the gas is going to expand, yeah, to a final volume. Okay, I'm just checking myself. All right, so now we need to solve that equation in one unknown. These negatives are going to cancel. And what we need is to multiply this times that equals 0.8355 final volume minus 0.3 value. And that's 0.259. 0.259 is this one times that one, and this one times that one is this one. It's 9.23. So now we can get this one on that side, which make it positive. Add that value to 9.23. Okay, 9.49. So this is 9.49 equals 0.38355 final volume. Now all we have to do is divide both sides by 0.8355. And that's 11.4. So the final volume is 11.4 liters, which is C. Okay? All right. And let's see. Let's go down to number 12. Calculate the work associated with the compression of a gas from 121 liters to 80 liters at a constant pressure of 13.1. That's repetition, except that the answers are given in both positive and negative values. So if you miscalculate, you might get the number right, but the sign wrong. So let's go ahead and work this one. Compression of a gas from 121 to 80 liters. So the final volume is 80. And the initial volume is 121. Okay, there. Under a constant pressure of 13.1 atmospheres. We do the calculation. Negative pressure, final volume minus initial volume. Okay, how much work? Calculate the work associated. See, it didn't tell us whether the work is on the system or on the surroundings. You have to tell that from the calculation itself. And if you get these in the wrong order, you'll get the wrong answer. So 121 and 80 is a negative 41. Right. This is a negative 41 times 13.1 is 53.7 liter atmospheres. Oops. No, I'm sorry. Decimal's in the wrong place. 537 liter atmospheres. So it's positive, and that means that the gas is doing work. No, work is being done on the system. It's a positive value. So B is the answer here. Okay. All right. Let's see. That was 12. Let's do, let's go to 14. 14 through 17 are based upon that scenario at the top. So let's put that up there first. Consider a gas in a 1 liter bulb. A 1 liter bulb at standard temperature and pressure. Right? For gases, standard temperature is 0 degrees and pressure is 1 atmosphere. Right? 1 atmosphere. Okay. Oh, it's connected. It's connected to another bulb with a valve. Only this bulb, doesn't say what size it is, doesn't matter. This is at a vacuum. Okay? Now, what happens when the valve opens? Well, obviously, when the valve opens, gas is going to flow from here to here until it equalizes the pressure. And we don't have to know exactly what that value is, not to answer the questions. 14. What is true about the value of Q? Is it greater than 0, equal to 0, less than 0? What is the value of Q? Well, how do we measure Q? A transfer of heat. Is any heat being transferred? No, the gas is just expanding into that space. If it's at standard temperature the whole time, no heat is being transferred at all. Q equals 0. How about 15? What is true about the value of W? Well, W is work. It's force applied through a distance. Is there any pressure? Is the gas expanding against a constant pressure? Well, no, there's pressure here, but it's not expanding against a pressure. The pressure is going to drop, obviously, right, as it expands, but it's not pushing against any pressure. The pressure is not constant. So the work, there's no work being done at all. What's true about the value of internal energy? 0 plus 0 equals 0. Right? Internal energy change is 0 also. We're going to get to this problem not in this course. It's in the second semester, where we find a way to rationalize, if nothing else, what has happened here, right? Because there's no driving force there. I mean, why is the gas moving at all, right? Based on what we know now, it shouldn't move. But we'll get to that next semester. What's true about the value of delta H? Well, delta H is enthalpy. It's a measure of heat potential. But if Q is 0, delta H has to be 0. It can't be anything else. Right? There's no potential for heat movement there at all. Okay, so all those values are 0 under this scenario. Let's go ahead and do 18. Just a little thought problem. Of these two, well, I gave it away. Of energy, work, enthalpy, and heat. Energy, work, enthalpy, and heat. How many of these are state functions? This is a state function. This is a state function. These are both path functions. It does matter how you get from point A to point B. But for these, it doesn't matter. So the answer to that one is 2. Only 2 of these are state functions. Let's see, how are we doing on time? Normally we start, okay, we got another hour and 15 minutes. Let's see, what do I want to do next? 19? 19? Yeah, well, this is a good definitional problem. Okay, of these properties, which are intensive properties? Mass, let's see, that's a 1, 2, mass, temperature, 3, volume, concentration, and energy, which are intensive properties. Which ones, it doesn't matter how much of the substance or stuff is there. Mass, right, it does matter. That's an extensive property. Temperature, doesn't matter how big the mass is, at a given temperature, you can have 100 tons of it or you can have 5 grams of it. It's still the same temperature. So this one, yes, this one's intensive. How about volume? Right? Volume is an extensive property because the more volume you have, the more you have of that property. Concentration, that's an intensive property. It doesn't matter how much of the solution you have or whatever the case may be, it's still the same concentration. So that was one. How about energy? Energy varies with amount, so it's an extensive property. So there are really only 2. 2 and 4. So that's why the answer is C. 2 and 4 are intensive properties. All right, let me see. Let's go down to 22. So for this balanced equation, the combustion of ethanol or ethyl alcohol, which of the following is true? Let's see. Yeah, I guess I better write this one up here so I can talk about it. And it's a combustion because we're combining it with oxygen, correct? 2 CO2s and 3 waters. And the delta H is minus 137. 1.37 times 10 to the third kilojoules. Right, so it's a fairly energetic reaction. All right, what about these possibilities? The reaction is exothermic. Is it exothermic? Yeah, right there. That's exothermic. How about 2? The enthalpy change would be different if gaseous water was produced. Would this value be different if this were a gas instead of a liquid? It's a liquid this time. Right? I didn't write the phases, but I need to. All right, think of it this way. What is the gas? What will be the products of this reaction? If ethanol reacts with oxygen to make carbon dioxide and water, and it's exothermic, that's enough heat that this product should be a gas. Well, if we make it a liquid under standard conditions, what has to happen? If you go from a gas to a liquid, that is an exothermic process, right? So delta H is going to be more negative. So this value should be more negative than it is if this were a gas. No, excuse me. It would be less negative because we subtracted that out, right? From going here to here. If we go from here to here, then that becomes positive. Right? So now if it's a gas instead of a liquid, then this value should be less negative. But the change would be different. Right? So that one is also true. How about 3? The reaction is not an oxidation reduction one. That's false. Anytime you have a combustion, that's a redox. Electrons must be transferred in a combustion reaction. Okay, so 4. Right, so that was out. 4. The products of the reaction occupy a larger volume than the reactants. The products occupy a larger volume than the reactants. Okay. Well, this is a liquid, right? So its volume can be considered negligible. This one's a liquid, it's negligible. So all we have to do is compare this one to that one, right? All things being equal, you start off with 3 moles of gas and you end up with 2 moles of gas, right? If you're going to keep the pressure constant, then 2 moles are going to occupy less volume than 3. So the products of the reaction occupy less volume than the reactants. That was false also. Based upon that reasoning, comparing those gases. Okay, so the answer is A, 1 and 2. That took a little work. '22. All right, let's see. I have another one marked off. How about 24? Yeah, 24. This is a calorimetry problem. Well, it speaks to specific heat and the heat transfer. How much heat is required to raise the temperature of 5.75 gram sample of iron? So the mass of iron is 5.75 grams with a specific heat of 0.45 joules, yes, joules per gram degree C. From 25, so initial temperature is 25 degrees C. Final temperature is 79.8. Okay, so how do you figure that out? Do we have all the information we need? If we use, let's see, let's just say Q. Heat change is specific heat times mass times change in temperature. So this is what we're after. What's the heat change? How much heat is required? So this would be 0.450. I'm going to leave out the units because we got all the units right. Joules, grams, degrees C. We're good on the units. Mass, 5.75. And change in temperature, final minus initial, 79.8 minus 25.0. So we just need to get out the calculator. And let's do this one first. 79.8 to 25.0. So that's 54.8 degrees C difference times 5.75 and then times 0.45. And I get three significant figures. One, is that right? Yeah. 142 joules. It takes that much heat to do what the problem says it should do. That's why the answer is E. Be sure you know how to work these problems. Because if you see a problem like this on the test, it may not have the same parameters, but it may have the same approach. So be able to work the problem. That was 24. Let's see, how about, yeah, let's do 26. 26 is an actual calorimeter problem. All right. So we have a 32.5 gram piece of aluminum with its molar heat capacity. And it's heated to 82.4 degrees and dropped into a calorimeter containing water with its specific heat capacity, initially at 22.3 degrees. The final temperature of the water is 24.2. Calculate the mass of water in the calorimeter. All right. I noticed one thing about this problem. They're ignoring the heat capacity of the calorimeter itself. We're just don't consider it. So what we have is an isolated system, right? An isolated system, which means all the heats have to add to zero. We have a Q that's attributed to the aluminum, and we have a Q that's attributed to the water. And we don't have a Q for the calorimeter, which we, in real world, we would have. Okay. So these terms can be separated out as S, molar S for aluminum. Then we need moles of aluminum times a change in temperature. Okay, so what are we given for aluminum? 32.5 grams. We need to convert that to moles. How do you do that? Molar mass. So let me see, what's that for aluminum? 26.98. So let's take 32.5 and 26.98, divide that into it. 1.205 moles of aluminum. 1.205 moles. Oops, wrong place. Wrong place. This one is 24.03. 24.03 joules per mole degree C. There we go. And moles is 1.205 of aluminum. What's the temperature change? Final minus initial. What's the final temperature? It's the temperature of the water at the end of the experiment, 24.2 degrees. What was the initial temperature of the aluminum? 82.4. Okay, that's the aluminum term for heat. Now let's do water. Let's see. Heat capacity for water is 4.185, I think. They're only going 4.18. All right, so let's do it that way, because the answers might be different if we do that. 4.18 joules per gram degree. What's the mass of the water? It's unknown. What's the temperature change? Final is the same temperature, right? Because the metal and water are now at equilibrium. And what's the beginning temperature? 22.3 degrees. Okay, now we have an equation. I didn't write the rest of this out here. This would be specific heat for water plus the mass of the water times delta T for the water. Okay, so now what we have to do is solve, right? The thinking part is done. This is all the thinking required. The rest is just number crunching. So let's take this term and reduce it to one number. 24.2 and 82.4 subtracted from it times 24.03. So this one is minus, right? That's a minus. 1.685 times 10 to the third. This is degree C, canceled. This is moles, canceled. So that value is in joules. This one, we have a value over here, 24.2 minus 22.3 is 1.9, right? Times 4.18 is 7.492. 7.492 times the mass of the water. Okay, this needs to go on the other side. Remember how to solve algebraic equations. You get everything on one side that's not unknown and leave the unknown on its own side. All right, so that makes this positive. And then to get this, at that point, you divide that one by this one. Now that's positive 1.68. Let me flip that around, change the sign. Okay. Then you divide by 7.492. So I get 225 mass of the water equals 225 grams. And what did I do wrong? Right? It says the answer is 212. Let me check my math. Right? That's right there. Is this right? 32.5 grams of aluminum. Yep. And then divided by 26.98. I know that's right. 1.205. That's right. How about this one? 24.2 and then 82.4. So that's 58.2 degrees C, negative 58.2 times 1.205 times 24.03, 1.685 times 10 third. That's right. How about this one? Is that 1.9? Yeah, that's 1.9. 4.18. 7492. This goes on that side, becomes positive. And then we divide by this one. Oh, I don't know how it happened, but I must have hit the wrong keys. That's right, 212 grams. So the answer is A. Okay, that was a lot of work, I know. That's why you have to be very methodical about your approach. Know where you're headed and check yourself at every potential point of error. Always be questioning yourself along the way. I know that's hard to do in the heat of an exam, but if you practice it at home, then it becomes more second nature. All right, so let me see. How are we doing? We're doing okay. 27. Let's see. That was a calorimeter problem. That was a hard one. Let's do an easy one to kind of relax our brains. Number 32. In the lab, you mix two solutions, each originally at the same temperature. And the temperature of the resulting solution decreases. Which of the following is true? So you have this one and this one, both at a temperature, same temperature. Then when you mix them together, the resulting temperature final, is less than the temperature that you started at. Okay, now we can ask our questions. The chemical reaction is releasing energy. A, false. It's absorbing energy. Temperature is decreasing, so it would absorb energy from its surroundings. B, this energy released is equal to Sm delta T. The energy released. Well, no, we just said it's absorbing energy, so it doesn't matter what the formula is. It doesn't release energy, right? So B has to be false. Regardless of the equation doesn't matter. The words energy released are wrong. C, the chemical reaction is absorbing energy. True. It's an endothermic reaction. The chemical reaction for D says it's exothermic, right? That's false. So there's just this one that's true. All right. So now that was fairly easy. Let's see, where can we go from here? Let's see. What about let's skip that one. How about 38? Okay, 38. On a cold winter day, a steel metal fence post feels colder than a wooden fence post of identical size. So we got a steel post, which is essentially iron, and we got a wood post. Okay. And this one feels colder. Okay, why is that? Well, it looks like the answers are referencing specific heat of the steel versus the wood. The mass of, well, let's work backwards. D says because the mass of the steel is less than wood. Well, is that true first? They're identical sizes, but we know that steel is denser than wood, right? So D cannot be true, right? Regardless of the heat change, right? Because it says that the steel weighs less, has a less mass than the wood. That's false. So we can throw that one out. How about, let's compare. Let's get to this point here. Feels colder. What does that mean? That means temperature, the heat is being transferred out of your hand. Right? Heat is being transferred out of your hand. So Q is going like this. And the same thing for wood. But we're seeing the difference. More heat is being transferred to the iron, and it feels colder because the temperature change is less. Temperature change is greater. So the temperature change on this side is greater than the temperature change on that side. So the temperature change of the steel is greater than the temperature change of the wood. Okay, that's the key. It feels colder because the temperature change is greater on this side. All right, now let's see what that means. Well, Q for the steel is equal to S M delta T. And the Q change for the wood is S, and this is, they have different specific heats. That's obvious. They have different masses also, right? So there's a mass of iron and there's a mass of wood. And how about the temperature change? Right? Well, the temperature change for this one has to be greater than that one. So this one is greater right here than that one. Okay, we've got a bunch of variables going on here. Something has to be held constant in order to make the comparison. If this temperature change is greater, if this increases, notice that these are products. So let's say we hold the amount of heat constant. Say these are equal. The masses are different. So we can't deal with three variables. So let's say this is one variable right here, and this is another variable. So if this is larger than that one, then this one has to be larger than that one. This one has to be greater than that one. Correct? This one has to be greater. Right? In order for these to be the same, as this one goes down, this one has to go up. This one has to be greater if that one's greater. Okay, so if we know now that this one's greater than that one, why is it greater? Well, the mass of the wood is much, much less than the mass of the iron. Right? So the specific heat of wood must be greater than the specific heat of iron. Right? If this one's greater than that one, but this is less than that one, then the only way that that can be true is for this to be much greater than the specific heat of iron. Now let's look at our answers. A, the specific heat capacity of steel is higher than the specific heat capacity of wood. Nope, it's the other way around. B, the specific heat capacity of steel is lower than the specific heat capacity of wood. Yes, lower than wood. That's true. B is true. But are two of them true? Well, we know that B is true. Right. That one's true. Let's look at C, because if both B and C are true, then E is the answer. So let's look at C. Steel has the ability to resist a temperature change better than wood. What does that mean? What that statement means is a measure of the temperature change with the amount of heat is specific heat capacity. So if that were true, steel has the ability to resist a temperature change better than wood, means that the specific heat of steel would have to be greater than wood. And we know it's not. The specific heat of wood is greater than steel. So C is also false. That means B is the only possible answer. We had to dance around the barn several times to get that one. All right. Let's see. That was 38. Let's see. I'm trying to find something unique, something we haven't covered. How about how about 43? That takes us back to this burning ethanol, but it asks a different question. And it introduces it tests our understanding of the concepts of stoichiometry. Right? So if we have this equation, 43, let's see, C2H5OH plus 3 oxygens yields 2 carbon dioxide plus 3 waters, I think. Yeah, and the delta H is equal to minus delta H is equal to minus 1.37 times 10 to the third kilojoules. The question is, if you have a 21.1 gram sample of ethyl alcohol, right, and we have to assume that oxygen is excess. Otherwise, we can't work the problem. And the molar mass of ethanol is 46.07 grams per mole. We will need that. How much energy is released? Well, we know energy is going to be released because it's negative. The delta H is negative. But what's the process here? Well, remember when they write this value out here, it's for that equation as balanced. So this is that many kilojoules per mole of ethanol. And since that's the beginning point, then that's the way we interpret that value. But we need to know moles, right? So we need to convert that many grams of ethanol into moles using 46.07 grams per mole. Okay, so let's take our calculator, 21.1, right? And 46.07 divided is 0.458 moles of ethanol. That's my abbreviation for ethanol. OH always means alcohol in abbreviations, and ET is short for ethanol. So that's my shorthand. Okay, this is how many moles. And this is how many kilojoules per mole. So if we take that and multiply by this per mole of ethanol is minus 1.37 times 10 to the third kilojoules. That'll give us our answer in kilojoules. And it looks like, yes, the selections are all in kilojoules. So we just need to do this math. Let's see, 1.37, change the sign, exponent 3 times. So I get minus 627 kilojoules, or 6.27 times 10 to the second. And that appears to be C. Okay? All right. So I better look to see if there's anything that we have not covered yet. I don't want to run out of time because I want to stop at no later than 3 o'clock. Right, 3 o'clock. Yeah, to talk about the lab a little bit. So let me leaf forward and see. Oh, we haven't done anything on Hess's law yet. Let's see. Let me pick out a Hess's law. I'd rather do a real one rather than these ABC things. Okay. How about this? Will take some doing. How about 59? You have to be very, very methodical about this one. And fortunately, I got a lot of board space to work with. 59. Right? When you're working a Hess's law problem, you want to find the enthalpy for a reaction based upon the several reactions that you combine. You start with the target reaction first. And that tells you which ones of the other reactions are going to be useful in getting to your goal. So to calculate the delta H for the reaction below, that's P4O10. Let's see, P4O10. We better put the phases in there. Sometimes the phases matter in these types of reactions. So this is a solid, and we're going to react it with 6PCl5, is it? Gas. And that yields 10Cl3PO. 10Cl3PO. And that is also a gas. Okay. So here are the reactions we have to work with. Roman numeral 1. Let's look at it first. Does Roman numeral 1 have anything in it that we need? There's P4, nope. Cl2, nope. PCl3, nope. We don't need 1 yet. We might need it later, but not right now. Let's look at Roman numeral 2. P4, nope. Oxygen, nope. P4O10, there it is. We do need number 2. Well, number 2 is, we're starting off with P4 solid plus 5O2 gas, obviously, and P4O10. P4O10 solid. And that has an enthalpy of minus 1225.6. Minus 1225.6 kilojoules. Right? These are delta H's. Okay, first off, notice this is on the wrong side of the equation. It needs to be over here on the left side of the arrow, right? But this is exactly how many we need, just one of those. So all we have to do is flip the equation. Like that. P4 solid. 5O2 gas. Now what happens to this value? Reverse the sign. Okay, so that one is fixed. We got that covered with this. And we're going to use that equation and this enthalpy change. Okay, how about 3, PCl3, PCl3, nope. Cl2, nope. PCl5, there it is. We do need number 3. And it goes PCl3, Cl2, PCl3 plus Cl2. And oh, those are gases. Yields PCl5, PCl5 gas. And the enthalpy change for that is minus 2967.3. Minus 2967.3 kilojoules. All right. Same problem. Actually, more than the same problem. This is on the right-hand side of the arrow. That's on the left-hand side. So we do have to flip the equation. But we also need 6 of them. So we need to flip the equation and multiply it by 6. We need to go that direction and multiply by 6. So we're going to have 6 PCl5 yields 6 PCl3 plus 6 Cl2. Now, what happens to this value? Well, the sign changes, yes, but we also have to multiply it by that factor, 6. So 2967.3 and 6 times. So we get 1 3.8 kilojoules. 6 times that. 6 times 3 is 18. Yeah. Okay, so we're going to use that one and that one. All right, so we took care of this one and that one. Now we need Cl3PO. And that's number 4. So the equation as given is PCl3, PCl3 gas, plus 1/2 O2 gas yields what? Cl3PO, Cl3PO gas. And the enthalpy change as written is minus 285.7 kilojoules. Now let's compare it to our target equation. Okay, we have it on the right, it's on the correct side, but we need 10 of them. Right? So we're going to end up with 10 PCl3 plus 5 O2, right? 10 times a half, and 10 Cl3PO gas. Okay, that takes care of this one. What do we do with this value? Multiply it by 10. And we don't have to change the sign because we didn't flip the equation. So this one is 2857 kilojoules negative. So we're going to use that one and this one. Okay. Now, see what we've done. We got this one here. We got PCl5. We got this one here. And we got this one there. So what have we done? We've added that one, this one, and this one. And we've added this one and this one. All right. Now, this one cancels this one. That's on the right-hand side. This is on the left-hand side. So the oxygens cancel. How about the chlorines? Right? Or the phosphorus? Or the PCl3? Well, this one is on the right-hand side. So it cancels 6 of these and leaves us 4 of those. All right. So now we go back to Roman numeral 1. And Roman numeral 1 says P4 solid plus 6Cl2 gas yields 4 PCl3. PCl3 gas. And the enthalpy change there is 1225.6. Oh, wait a minute. No. Oh, you know what? I put the wrong value here. This one is 2967.3. Hold on a second. Hold everything. I got everything out of whack here. So let's start over on these. The equations are right. We went to number 2, 2967.3 minus 2967.3 kilojoules. And all we did was flip the equation, right? So this is positive 2967.3. Okay. The second one PCl3 is Roman numeral 3 minus 84.2. Minus 84.2. We flipped it and multiplied it by 6. Right? Yeah, we flipped it and multiplied it by 6. So that's 505.2 plus 505.2 kilojoules. There we go. And this one, we left it alone, but we multiplied by 10. So that was number 4 minus 285.7. Minus 285.7 times 10 is minus 2857 kilojoules. Okay. Now for the last one. That's minus 1225.6. And what do we need to do to it? Oh, yeah. Well, is everything on the right side that it needs to be? Well, there's P4, right? So that cancels. I think it's on the right side. And there's 6 chlorines. 6 chlorines. Right? How about PCl3s? See there, there. Here, 4 PCl3s. We didn't have to do anything to that value. Okay, so now we can add this one, this one, this one, and this one. And that should give us our delta H for the target. Let's see, 2967.3, 505.2, 2957 subtracted, and 1225.6 subtracted. So I get minus 610. And that's B. The best answer for that one is B. Okay, that one took a lot of work. There's no doubt about it. And I wasn't as careful as I said you should be, because I got these in the wrong place. All right.
Still looks like a mouth.
Okay, that was 59. Let's see. I want to do one with using heats of formation. Let's see. Heats of formation. Okay, 65 is a good one. There was another one in here I wanted to get to also. Just a second. Okay, that'll work. 65. There we go. Yeah. Yeah. 65. Okay. First of all, when it says, it gives you a couple of reactions up there, but you don't know what to do with them because there's no target equation. You've got to create the target equation. Calculate the standard enthalpy of formation for copper 2 oxide solid. So how do you write the standard enthalpy of formation equation? You start with the product. And then you go to the reactants. And the reactants have to be the elements in their most stable state. Copper, oxygen. Okay? Then you balance them. You don't touch the coefficient on this side. Right? It's chiseled in stone. You have to use, if necessary, use fractions on this side. So we got one copper, one copper. We need one oxygen. That's your target equation. Now, let's see what we've been given. Copper 1 oxide solid. Copper 1 oxide solid plus a half of oxygen yields what? 2CuO. 2CuO. Okay. And the enthalpy change is, let me get my cursor out of the way, minus 144. All right. So is everything where it needs to be? Well, this can only address that one right there. But it needs to be, well, let's look at this. Notice that those two equations both have copper 1 oxide on the left. But the target equation has, there's no place for copper 1 oxide. We got to get rid of that copper 1 oxide. So instead of focusing on this one, let's focus on that one. This is the other equation. And that's endothermic, 11 kilojoules. Notice that if we flip this equation, that puts copper on that side and copper oxide on this side to cancel one of those, and puts this one on the other side. Because we've got oxygen here, and we've got more than we need here. But if we flip the equation, that puts copper over there on that side. So let's do that. We're going to use this equation, and we're going to flip this one. All right, now this becomes negative. There we go. Now, this one cancels one of these. All right, we're using this equation and that equation, not this one. Yeah. So that takes care of this one and takes care of this one. Those two are good. All right. That's good. And this one cancels that one. And this one canceled one of those, leaves us with this one. So we're good there, we're good there. All right. The way I look at it, we can add now. So we add minus 11 to minus 144, which should be minus 155. Minus 155 is E. Okay. Minus 155 then is the heat, the enthalpy of formation for copper 2 oxide. Okay. That was a hard one. Let's do an easy one. How about 68? Choose the correct equation for the standard enthalpy of formation for carbon monoxide, where the heat of formation is given as minus 110.5. Right? So if you look at all those answers, every one of them has minus 110.5. So that's given. What we need to do is concentrate on the formula. So what's the standard heat of formation for carbon monoxide? CO, gas, 1 mole, always 1 mole. We need carbon here, which should be carbon. Graphite is the most stable form of carbon. And 1 oxygen here, so we need a half. So that's the equation. Carbon graphite plus a half oxygen yields carbon monoxide. And it looks like C satisfies that condition. Okay. That was fairly easy. Probably should have done that one first. All right. Let me see. Let me flip to my hard copy. It's easier to figure things out with the hard copy. Well, let me see. How about 78? That's another easy one. One of the main advantages of hydrogen as a fuel. Hydrogen. Well, actually, it may not be in that form. It just says hydrogen. We assume that it's hydrogen gas, right? Hydrogen as a fuel, right? What are the possibilities? The only product of hydrogen combustion is water. That's definitely an advantage. So if we do have hydrogen gas and we combust it in the air, that means we're reacting with oxygen and yields water. That's it. That can take several forms. But if we balance it, there, oops, excuse me. It's a 2. There we go. That's definitely an advantage. It exists as a free gas. Actually, that's not an advantage because hydrogen is extremely reactive. Existing as a free gas just makes it available for combustion when you don't want it to combust. So B is a disadvantage. C, it can be economically supplied by the world's oceans. Well, that's sort of an advantage, but what we're getting at with supply by the world's oceans is not hydrogen, but deuterium or tritium. And that's for nuclear fusion. Right? So that's not the best advantage because we have not perfected the fusion yet. Right? So that avenue of hydrogen acting as a fuel is not open to us yet. So the A is a better answer than C. Plants can economically produce the hydrogen needed? No. Plants take in carbon dioxide and spit out oxygen. Right? So that's not right. They don't give out hydrogen. E, it contains a large amount of energy per unit volume of hydrogen gas. Well, no, not per unit volume. Based on a molar, based on the moles, it's very efficient. And the only place that it's really an advantage is in rocketry, because hydrogen combined with oxygen produces a very high specific impulse. And we don't have time to talk about that right now, but it makes it a very efficient fuel for rockets. But that doesn't cover the whole economy. That's just one little sliver. So really, the best answer is the only product of hydrogen combustion is water. And that's because it's water and it's not carbon dioxide. Right? If we were to burn, say, methane or ethanol, C2H5OH, or even ethanol, or what else? Gasoline. Oops. Or diesel's even worse, right? They all produce carbon dioxide as a product. Now, at this point, I'm not going to argue the counterpoints to carbon dioxide as a greenhouse gas. It does produce a greenhouse effect, but it's not the major component. But that has no bearing on the question. The question is this the main reason for hydrogen as a fuel? And yes, it is. In fact, if we had a really cheap source of electricity, like from nuclear fusion, then we could take this water and run it through electrolysis and produce hydrogen gas again. Right? That's not balanced. But see, it's just an endless loop, and you get your oxygen back, you get your hydrogen back, and the only energy expense comes from nuclear fuel. And once you've used that, then you can use the hydrogen in lots of other places. All right, so that answers that as far as I can. Oh, let me see. All right, a lot of those problems at the end of the chapter are repetitions from the earlier parts of the chapter. I was looking for one, and I don't see one. One where we use the heats of formation equation. Right, if you want to know the delta H for overall for a reaction, then you need to take the summation of all the delta H's for products and subtract the heats of formation for the reactants. And I didn't see one like that in there unless I missed it. Let me go back through, let me flip back through the pages and see if I missed one. Nope, not there, not there. Not there. Well, it escapes me. I don't see one in here at all. Okay. Well, if you run across a question like that, what you have is, I'm going to have to be general here. Oops. D, C, B, A. These are the coefficients, right? Little a, little b, little c, and little d. So you would take the heats of formation for C and multiply it by the little c. That's what this means. And then the heats of formation for D, multiply it by little d. And then subtract A times the heat of formation of A and the heat of formation for B times its coefficient. And that would give you the heat of formation, the standard enthalpy for that equation. Once this equation is balanced, then you have the coefficients that fit in these places right here. Remember, this is sigma, which means summation. So you sum any of the products, each one of these, as many as it takes for products, and then subtract reactants. Since I can't find a problem, then I'm going to have to leave it at that. All right. So I think I'm done with the review.